Hi everyone, so this is chapter 2.1 of the Year 2 Pure Maths book. Chapter 2 is on functions and graphs, and the chapter 2.1 is on the modulus function. So there's just some notes to make before we do the examples in this subchapter. So the modulus of a number a, so the modulus of any number, is written as, it's written like this. So you can see the number a with two vertical lines either side of it. That means the modulus of a. Now the modulus of a is the non-negative numerical value of a. So it's the non-negative numerical value of a. So if the number a is non-negative anyway, if a is 5, then the modulus of a will also be 5 because it's the non-negative value, numerical value. Whereas if a was negative 5, then the modulus of a would actually be equal to 5 because it has to be non-negative. Now the modulus of a number is also sometimes called the absolute value of a number or a function. So just bear in mind that sometimes you'll see this term absolute value. Next is that for a modulus function, which would be written like this, y equals the modulus of f of x. And remember, f of x is just a function of x. It could be x squared, it could be 2x plus 3, it could be x squared plus 2x plus 3. It's just a function of x. But if we have a modulus function, then the values of f of x, or the values of the modulus of f of x, are not quite the same as when we're not working with the modulus function, obviously. So this will make more sense when we do the examples, but when that function of x gives a value that's greater than or equal to 0, so if I had 2x plus 3 and I substituted in 200, then it's going to give me a positive value, isn't it? It's going to give me 403. So when that function gives you a value of 0 or more, then the modulus of that function is just equal to the function. Because remember, the modulus is just a non-negative value of that thing. So if that thing gives you a positive value or a 0 or a value of 0, then it's just equal to the function itself. So the modulus is just equal to the function itself. However, if we have a situation where that function gives us a negative value, so I'll stick with my example of 2x plus 3. If I substituted in negative 200, then I'm going to get negative 397, sorry. So in that case, when I substituted x was negative 200, f of x was negative. Now remember, the modulus of a function or a number has to be the non-zero numerical value. So in this case, where your function gives a negative value, the modulus of the function is equal to the negative of that. So in my case, with 2x plus 3, I substituted negative 200, I got negative 397. My modulus will be the negative of that. And the negative of negative 397 is positive 397. So essentially, you're always taking the positive value of the thing that you're working with, whether it be just a number or a function. This will be made so much clearer in examples 1 and 2, so we'll do those now. So we first have example 1, and this is on page 23 of the book. So example 1 asks us to write down the values of the modulus of negative 2, the modulus of 6.5, and the modulus of a third take away 4/5. Okay, so remember, the modulus is just a non-negative numerical value of whatever's inside our modulus lines, brackets, I don't know, they're not brackets, but you know, those things. So for this first one, well, the modulus of negative 2 would be 2, because it has to be the non-negative value of whatever's in here. For the next one, the modulus of 6.5 is just 6.5, because it's already positive, so that's fine, we just take the non-negative value. Now for the next one, we're just going to have to work out what a third take away 4/5 is. So, okay, let me do that over here. So we'll have to change our denominators both to 12. Oh, sorry, no, 3 and 5, 15. It's 2x. So we'll have 5 over 15 over here, and then we'll have 12 over 15 here. And when we subtract those, well, 5 fifteenths take away 12 fifteenths gives us negative 7 fifteenths. So what this question actually wants is the modulus of negative 7 over 15, which we must take the non-negative value, so it would just be 7 over 15. So hopefully that makes sense with the numerical examples. So I'm going to just move down the page now to do example 2, where we'll be looking at what we were describing here when you have a function. So example 2, we're given a function f of x equals the modulus of 2x minus 3 plus 1. So, and then for part A, we need to write down the value of f of 5. For part B, we need to write down the value of f of negative 2. And for part C, we need to write down the value of f of 1. So, we'll start with part A. So we're first going to substitute into our function the number x equals 5, the number 5. So we're going to have the modulus of 2 times 5, which is 10 take away 3, all plus 1. And 10 take away 3 is 7. And then the modulus of 7 is 7, because it's already positive. So this is going to just be 7 plus 1. So our answer here is 8. I might highlight these. For part B, we want to find f of negative 2. So we're going to substitute that into the function. We're going to have 2 times by negative 2, which is negative 4. Take away 3. And then plus 1 on the end. And that's the modulus of negative 7 plus 1. Now the answer here, well, the modulus of negative 7 is 7. It has to be the non-negative value. So we're just doing 7 plus 1 again for this one. So the answer to f of negative 2 is also 8. So for this function we've been given, f of 5 is equal to f of negative 2. They both give you 8. And for the last one, we're going to substitute in 1. So 2 times 1 is 2 minus 3, all plus 1. And then 2 take away 3 is negative 1, plus 1. And the modulus of negative 1 is just 1. So 1 plus 1, and that's 2. So hopefully that makes sense with our modulus of numerical numbers and modulus of functions here. So what I would suggest now is that you pause the video and go to the exercise 2A, and do questions 1 and 2. And then I would come back to the video, and then we'll go on to the next thing. Okay, so next we're going to look at sketching graphs of modulus functions. So just a couple of notes to make here before we do the next example. So to sketch the graph of a modulus function, so here we've just given a generic one, y equals the modulus of ax plus b, so that would be a linear graph. We follow 2 steps. The first step is that we sketch what that graph would look like just normally with no modulus. And then what we do is we reflect the section of the graph that's below the x-axis in the x-axis. So I'm going to show you what this means just for a really simple function. So we're going to sketch the function y equals the modulus of x. Y equals the modulus of x. I've given myself 2 axes here, but I wouldn't usually do that. It's just for this. To be honest, I should have just used one, but anyway. So I'm going to follow the first step. I'm going to sketch just the normal function without the modulus. So we know how to sketch the graph of y equals x. Y equals x is just a nice diagonal line right through the origin. Now a tip, because for every question you do, you don't want to be drawing 2 sets of axes. So I'll show you what I do to get this all done on one set of axes. So I start to sketch my function, and remember this is a sketch. You don't have to find values and make it, it's a sketch. So I start to draw the graph. Now here, so I'm drawing my line, make sure my pen's going, and I'm approaching the x-axis. Now, when I start to move below the x-axis, I change my solid line, so this is a solid red line at the moment, I change it to a dotted line because I know that for the modulus function, I'm actually not interested in this part of the graph below the x-axis. Now that's really faint. I'll try and make it a little bit less faint. So as soon as I start to move below the x-axis, I change that into a dotted line because yes, this is the graph of y equals x, but I'm aiming to sketch the graph of y as the modulus of x. And then what I do is I follow the next step. So I reflect the section of the graph that's below the x-axis in the x-axis. So this is going to be reflected in the x-axis. So I think to myself, okay, well this point here, it might be, 3, negative 3, and I'm going to put it up here at 3, 3. So I draw myself a little dot, and then I connect it to the graph. So this solid red line here is the graph of y equals the modulus of x. And I leave my dotted line there. That was just, helping me to plot this. So I'm not actually going to use my second set of axes, and obviously for every question you do, drawing 2 sets of axes is going to take you ages. So we'll do example 3 now. Example 3. So example 3 asks us to sketch the graph of y equals the modulus of 3x minus 2. So I'm going to draw myself a set of axes. Remember, this is a sketch. You don't need to do like XY tables. None of this needs to be exact. As long as your y-intercept's roughly in the right place and your gradient is, positive or negative, then you should be fine. So here's my set of axes. So we'll follow the first step where we sketch this function without the kind of modulus involved. And we're going to use my little tip where when we start to dip below the x-axis, we change to a dotted line rather than a solid line. So I'm going to start to do that. Now I'm just looking at this function. Okay, this linear graph, it has a negative y-intercept. So the y-intercept is negative 2, so it would be like here-ish. And it's got a gradient of 3, so it's a fairly steep graph. Okay. What I sometimes do as well actually is I just find out the root, so where it will intersect with the x-axis. So I'm just going to do that here. I'm going to make this equal to 0. And I'm going to find where it intersects the x-axis, so at 2/3. So let's say this is 2/3 here, where we are intersecting the x-axis, and the negative 2, okay, it's going to be way lower than that, so we'll say that this is negative 2 here. So I've got my y-intercept, I've got my x-intercept, and I'm ready to start plotting. So get my ruler out, so we're going to be going through these 2 points here, and remember, as soon as we start to dip below the x-axis, we're going to change to a dotted line rather than a solid line. So I'm drawing in my solid line. I've hit the x-axis at 2/3, and now I'm changing to a dashed or dotted line. So that's that. So that's the graph of y equals 3x minus 2. Now to do the modulus of that, what I'm going to do, just to make sure this is nicely done, I can see that this end of the graph is just kind of next to the y-axis there, and I'm also going to plot that the y-intercept of this graph, the modulus of 3x plus 2 minus 2, will be positive 2. And I've got that to be here-ish. So that is where I'm trying to intersect. So reflecting this line up in the x-axis takes me to here. So there we go. I've plotted the graph of y equals the modulus of 3x take away 2. So what I would suggest now is that you pause the video and you go and have a go at question 4 in exercise 2A to practice drawing these modulus functions. Okay everyone, so the next thing we're going to look at is solving equations that involve the modulus function, and the method that we use to do this is purely graphical. We use graphical methods to solve equations that involve the modulus function. So this is example 4 that we're looking at now. Now example 4 wants us to solve this equation. It's the modulus of 2x minus 1 equals 5. Now what we do to solve this is we first, on a set of axes, on the same set of axes as well, we plot y equals the modulus of 2x minus 1, which we just did in example 3, and hopefully you did question 4 of the exercise as well, so you should be really confident with that. And then we plot y equals 5, and then we look at where these graphs intersect. So I'm going to draw myself a set of axes. Okay, so my first step, as I just explained, is I'm going to plot the graph of y equals the modulus of 2x take away 1. So I'm going to be slightly less exact than, I'm not going to do my x-intercept and so on with this one. I'm not going to, plot the root, but I know that this graph, it has a gradient of 2 and a y-intercept of -1. So I know it's going to roughly be like here-ish. So I'm going to start by drawing a solid line. And as soon as I start to dip below the x-axis, I'm changing that to a dashed line. I'm then reflecting this in the x-axis, the dotted line part. I'm reflecting that in the x-axis, and I'm looking, okay, so that's going to go up here. And there we go. And now it's intersecting at +1. So this is my graph of y equals the modulus of 2x minus 1. I'm going to change to another colour. You can keep the same colour if you want, but I like things to look nice. So now I'm going to plot the graph of y equals 5. Well, that's nice and easy. It's just a horizontal line intersecting the y-axis at 5. So this is the graph of y equals 5. And you can see that we've got 2 intersection points here. So here's our first one, where y equals 5 intersects with just the normal part of the graph y equals 2x minus 1. And we've got this other intersection point, which I'll label B, where y equals 5 intersects with the reflected part of the graph. Now, solution. So we're trying to solve this equation. We're trying to find values of x that this equation is satisfied for. And we can see that we should be getting 2 solutions to this problem. So we'll first consider what's happening at A. And make sure you're labelling your work nicely and making sure everything is clear. So at A, the graph y equals 5, or the line y equals 5, intersects with y equals 2x minus 1. And it's the standard positive part. It's not the reflected part, is it? It's the part that was already in the positive. So the part that's already in the positive intersects with the line y equals 5. This equation, really easy to solve. We get one solution, x equals 3. Now let's consider what's happening at B. At B, the line y equals 5 intersects with the reflected part of the graph y equals 2x minus 1. It's the part that actually would have been negative had we not been plotting the modulus function, but we have actually made all of those values positive by multiplying them by -1. So for this part of the graph, all of the negative values for 2x minus 1 have been multiplied by -1 to get this part of the graph, and that intersects with 5 with the line y equals 5 there. So we're now going to solve this equation. So you can do a couple of things here. You can multiply out the brackets and get negative 2x plus 1 equals 5. What I like to do is I like to divide or multiply both sides by negative 1 and just get 2x minus 1 equals negative 5. But it's up to you. You can multiply out the brackets if you want to. So we get 2x equals, well, negative 5 plus 1 is negative 4. So x equals negative 2. We can look at our graph to sense check our two solutions. X equals 3, well, yes, that's roughly in the positive, fine. And x equals negative 2, yes, that's roughly in the negative, fine. So our two solutions here to modulus of 2x minus 1 equals 5 are x equals 3 and x equals negative 2. So what I would do now is pause the video again and go to exercise 2a and have a go at questions 5 and 6 where they get you to practice this skill over and over. Okay, so we're going to look at the last two examples now, examples 5 and 6. And in both of these examples, we are still solving equations that have the modulus function involved in them, but they're just slightly more complicated than the example 4. So example 5 asks us to solve this equation. The modulus of 3x take away 5 equals 2 take away a half x. And we're going to follow the same method as example 4. We're going to plot y equals the modulus of 3x take away 5. We're going to plot y equals 2 take away a half x. We'll look at the intersection points and solve the equations. And hopefully it's as quick and easy as I just described. So we'll get some axes drawn. And I'm going to start to plot the modulus function first. So the function y equals the modulus of 3x take away 5. So this function, it has a gradient of 3 and a y-intercept of negative 5. So it's going to be a fairly steep line, a bit like this. So I'm going to start to draw a solid line as I approach the x-axis, and then as I start to move below it, that will change to a dashed line. Then I will reflect the dashed line in the x-axis to get my modulus function, or the plot of my modulus function. So this is the graph of y equals the modulus of 3x minus 5. I'm going to switch my colour now, and I'm going to plot the graph of 2 take away a half x. So this is just a rough plot. So I'm just going to make sure my y-intercept kind of makes sense. So the y-intercept of my modulus function would be at 5, because this was negative 5, as it says in the function, and then so that would be positive 5. So this is going to be intercepting at 2, which is obviously slightly less than that. And this is also a much less steep graph, isn't it? Because of the gradient of negative a half. It's a downward slope, and it's much less steep. So this is obviously completely not to scale, but there we go. There's my plot of y equals 2 take away a half x. So I can see that I've got two intersection points here. I'm going to label them A and B. Now I tend to always label A as the part of the modulus function that isn't reflected, and then B as the intersection point where the modulus function is reflected. That's just what I like to do. You don't have to do it, but that's just what I like to do. So we're first going to consider what's happening at point A. Well, at point A, we have the modulus function that isn't reflected, so it's just the standard plot of 3x take away 5, and that's intersecting with the plot 2 take away a half x. So this is a really quick and easy equation to solve. Going to have 7 over here when we add 5 to both sides, and if we add a half x to both sides, we're going to have 3.5, or 3.5x. And then dividing both sides by 3.5, x is equal to 2. Great, that was quick. Now if we consider what's happening at B. So at B, we have the reflected part of the modulus function. So it's the graph of 3x minus 5 where all of the values are negative, but they have been made positive by being multiplied by -1. And that is intersecting there with just the graph of 2 take away a half x. So again here you can multiply out these brackets that normally I just like to divide both sides by -1 and get myself 3x take away 5 equals -2 plus a half x. That's just what I prefer to do, but it doesn't matter which one you do. So I'm going to add 5 to both sides, so that's going to give me -2 plus 5 is going to give me 3, and then I'll take away a half x from both sides, and that will give me 2.5 x over here. And then when I do 3 divided by 2.5, or 3 divided by 5 over 2, that gives me 6 over 5, or x is 1.2. Oh, why did I write 1.6? So x is 1.2, or x is 6 over 5 is fine. So the solutions to this equation here, the modulus of 3x take away 5 equals 2 take away a half x. The solutions to that are x equals 2 and x equals 1.2. Okay, so example 6 then is the last example in this chapter, and I'm going to try and fit it onto the bottom of this page because I feel like it's a waste of paper if I just go onto a whole new sheet. So just waiting for that to focus. We're going to do example 6 now. And example 6 wants us to solve an inequality. But again, the process is the same. So we're just going to follow the same process as before. It's just the end part's different, the final answer. So the modulus of 5x take away 1, we want to solve the modulus of 5x minus 1 is greater than 3x. So we're going to plot y equals the modulus of 5x take away 1. We're going to plot y equals 3x. And we're going to see where they intersect. Okay. There we go. So first I'm going to plot the modulus of 5x take away 1. So this has a gradient of 5, so it's a pretty steep graph. And the y-intercept is -1. So I'm going to look a bit like this. I'll draw it like that. So a solid line as I approach the x-axis, and then when I reach the x-axis, this will change to a dashed line. I then reflect the dashed line in the x-axis. So I'm just going to draw a point up here to where I'm kind of finishing. And there we go. Now, I know that this doesn't really look like a gradient of 5. This looks like quite a shallow gradient, but it doesn't really matter. I want my diagram to be clear rather than... why is it not 11? I want my diagram to be clear where these two intersection points are rather than be like truly correct to what the gradient would look like. So anyway, that's the graph of y equals the modulus of 5x take away 1. Then I'm going to plot the graph of y equals 3x. So this has a y-intercept of 0, easy, and it has a much shallower gradient, well not much shallower, but a shallower gradient than this one. So it's not going to be as steep as this graph, it's going to be shallower. So there we go. There's that graph. So that is the plot of y equals 3x. And see, this is why I tried to make my gradients not that steep, because I knew my intersection points would turn out quite close together. But it doesn't really matter, we can see them still pretty clearly. So my first intersection point, so this is in the non-reflected part of the modulus graph, the modulus function, A. And then my second intersection point here in the bit that has been reflected, I'll call B. So to find these intersection points, we will consider what's happening at A and at B. So at A, we just have the standard plot of 5x minus 1 intersecting with the plot of 3x. You see, I'm trying to write smaller here so that I can save space. So solving this equation is going to give me 5x, oh no, what am I doing? Going to take away 3x on both sides to give me 2x, and add the 1 to that side to give me 1. So we have x is a half, or x is 0.5. And then for B, we have the graph of 5x plus 1, or 5x minus 1, but it's the part that's been reflected, isn't it? It's all of these negative parts that have been multiplied by -1 to make them positive. So there we go. And that's intersecting with 3x. So I like to divide both sides by -1. So I'm going to add 3x to both sides to give me 8x and plus 1 to both sides. And I'm going to get x equals 1/8. I might keep this one as a fraction in that case. So we've got x is a half and x is 1/8 as our solutions. So, well, they're not our solutions because we found the intersection points, which is great. But what we actually want to do is solve this as an inequality. So what I then do, once I've got my solutions or my intersection points, I look back at what the inequality is actually asking of me, and it's asking for the solutions where the modulus function, so the red graph, is greater than 3x minus 1. So we want the red graph values to be greater than the blue graph values. So I'm first going to consider the first point A. Now at point A, if I zoom, hopefully it doesn't not focus. So I'm just about to write my solutions. So I'll write the word solutions. So for this point A, is it to the left of A or to the right of A where the red graph, the modulus function, is greater than the blue graph? Well, clearly it's to the right of A. So it's where we know that A, we've just found out that A is a half. It's for values that are bigger than a half that the red graph is greater than the blue graph. So our first solution is that x has to be greater than a half. Now we'll look at point B. So for point B, which is 1/8, is it for values bigger than 1/8? So in this region, where the red graph is bigger than the blue graph? Or is it to the left of B, where the red graph is bigger than the blue graph? Well, clearly it's to the left. It's for values smaller than B, values smaller than 1/8. So our next solution is that x is smaller than 1/8. So this is one of those questions, one of those solving inequalities questions where you get two separate inequalities. So that's all of the examples, and you should be ready to go on back to the exercise 2A and work on question 7 onwards.